Lesson 7.3.3, Hypothesis Tests for a Population Proportion, Lesson 3. Introduction. In this lesson, we will think more about hypothesis tests. We will also learn about errors that can be made during this decision-making process. Consider the following claim, drawn from a 2013 online article. 40 years after the U.S. Supreme Court issued its opinion on Roe v. Wade, a majority of Americans support its decision. Roe v. Wade was a landmark decision by the United States Supreme Court that established a woman's right to have an abortion. In December of 2012, Gallup.com and USA Today surveyed by phone 253 randomly selected adults living in the West region of the United States. Each person was asked if they self-identified as pro-choice, pro-life, or neither. Of those surveyed, 134 answered pro-choice. Okay, so let's use the sample data to test the claim that a majority of adults in the West region of the U.S. self-identified as pro-choice at the time of the survey. We will use the 5% significance level. Step 1, determine the hypothesis. The null hypothesis assumes a value for the population proportion, P. And the alternative states that P is greater than, less than, or not equal to this value. Give these below. Okay, so we always know that for the null hypothesis, P is going to equal something. That's always the null hypothesis. And then the alternative hypothesis, therefore, is always going to be an inequality. It's either going to be greater than, or less than, or not equal to. So what would it be? Now, the trick here is to notice the claim is that a majority of adults believe in something, right? So what does majority mean? Think about the word majority when we think about the majority of a class thinks we should do this. Majority means more than half, right? So this means more than half. So when we say a majority, 0.5 is going to be the key here. So the null hypothesis is that P is equal to 0.5. The alternative is going to be that P is bigger than 0.5. How do we know? Because again, the word majority, right? We know that's greater, and we know that had to be the alternative because the null hypothesis always has the equal sign. Okay, let's move on. It says, is this a left-tailed, right-tailed, or two-tailed test? Well, because we have a greater than sign above, that's going to be a right-tailed test. Okay? All right, so we know that when we shade, we're going to be shading to the right. So step 2, collect the data. In this step, we gather data from random samples, compute summary statistics, and verify criteria for approximate normality. The criteria for approximate normality require that NP is greater than or equal to 10, and n times 1 minus p are greater than or equal to 10. Are the criteria satisfied? So what is n times p, and what is n times 1 minus p? We're going to need our calculators for this part. So remember, n in this problem is the sample size, and if we look at the sample size, it says they sampled 253 people, right? So 253 people. So it's going to be 253 times, what's p? P is given in the null hypothesis, and remember, P is 0.5. Remember, we're always assuming the null hypothesis is true. So if you multiply those together in your calculator, you will get 126.5. What about 253 times 1 minus 0.5? Again, multiply these in your calculator. If you put the parentheses in right, you should get the same answer actually. And this is bigger than 10, and this is bigger than 10 as well. So yes. So it says, are the criteria satisfied? Let me put that on the next line here. It says, did the study use a representative sample? Yes. Because if you go back up here and you look, it says that they lived in the west region of the United States, right? So we got to be careful. This sample does not represent all Americans. However, it does represent people living in the west region of the United States because that's where they sampled from, right? So, yes, the sample is representative of the west region of the U.S. since the sample was random. So, if you put both of these facts together, the normality criteria is satisfied. I've been asked many times before by students, what happens if the normality criteria is not satisfied? Well, the thing is, if it's not satisfied, then you're not even able to use the normal model for this. And so you wouldn't really be able to calculate an answer for the p-value. So in that case, if I'm asking you to do all this stuff, you always know that the criteria is going to be satisfied. So we just want to make sure that you guys know how to show that. Okay? All right, so let's move on here. Let's look at part E. We have assumed a value for the population proportion P above. What are the sample proportion and sample size? Well, we know what N is, right? N is the sample size. This is 253. And what would P hat equal? Remember, P hat are the number of successes, which in this case are the number of people in your sample that are pro-choice, right? Because that's what we're talking about. We're talking about how many people are pro-choice. So if we look up here, it says that in the sample, 134 were pro-choice. So we know that this is going to be 134 over 253. So if I do that in my calculator, I actually end up with 0.5296, and so that rounds to 0.530. 0.530. Okay, so now let's go over to the next step. Step 3, assess the evidence. The z-score of the sample proportion is called a statistic. Compute the mean and standard error of the underlying sampling distribution, assuming the null hypothesis is true. So we know that P is 0.5 if we assume the null is true, and that's the mean. What about the standard error? This is going to be the square root of P times 1 minus P divided by 253. So if we put all of that under the square root and hit enter on our calculator, I get 0.031. Please make sure when you use your calculator you get the same answer. Okay. All right. So let's compute the test statistic now. This is the same as finding the z-score. So remember, for the z-score, we're going to do 0.530 minus, that's p hat, right? And then minus the mean, which is 0.5. And then we're going to divide that by 2. Oh, no, sorry. Wrote that wrong. We're going to divide it by 0.031, right? The standard error. Okay, when I do that in my calculator, I get 0.97 if we round it to 2 decimal places, which usually for z-scores we round it to 2 decimal places. Is that unusually high? Remember, usually we say that something's unusually high when we have a z-score that's more than 2 standard deviations, and this is not even 1 standard deviation. So I do not expect that this is going to be strong evidence, but let's keep going just to make sure. The p-value is the probability of observing a test statistic that is at least as extreme as the one above. On right tail tests, the p-value is the area to the right of the test statistic. On left-tailed tests, the p-value is the area to its left. On two-tailed tests, the p-value is twice the area to the right of a positive test statistic or to the left of a negative test statistic. Remember, we talked about right-tailed, left-tailed, and two-tailed last time. Shade the region that represents the p-value below. Okay, so we want something at least as extreme as what we just found. So we know that 0.97 standard deviations is what we got. So if we want to go beyond that, it's going to look like, so 0.97 is right at the 1 mark, slightly to the left, and then we shade this way, right? Anything over there would count of being at least as extreme as that one. Okay. Use tables or technology to compute the p-value. Remember, we're looking for the area under the curve. We can use normal CDF on our calculator for that. So what would the lower limit be? The lower limit would be 0.97, right? That's the left of where we start shading. And it goes to the right forever, doesn't it? And so we're going to go until 1E99. Okay, so let's cut over to the calculator to see how to enter that in. So let's put this in our calculator. Let's see what we get. We're going to do second DISTR. I'm going to go down to normal CDF, and then I have 0.97 for the lower, and for the upper, 1E99. Hit enter twice, and I get 0.166. So we get 0.166. We don't even need that many decimal places. We could have written it instead as 0.17. So recall, when the p-value is small, the sample proportion is statistically significant. Keep in mind that even if the p-value is not less than the level of significance, it can still be small. Is the sample proportion statistically significant? And what does this say about the sample proportion? Well, let's go back to the level of significance they wanted, because the problem will always state. Okay. Now notice here it does say using a 5% significance level. So that's what we're comparing this number to. Okay. So notice that 0.17 is larger than 0.05. Okay? What does this mean? This means that the sample proportion is not statistically significant. And then it says, what does this say about the sample proportion? This means the sample proportion is not unusually high. Right? I mean, if we look here at the picture, we can clearly see that it wasn't that weird, the value that we got, right? It wasn't even one full standard deviation away from the mean. It's definitely not weird enough that it would lead us to reject the null hypothesis. So step 4, hypothesis tests are all about making decisions. We use the p-value to make a decision about the null hypothesis. Recall that if the p-value is less than or equal to alpha, the evidence is strong enough to lead us to reject the null hypothesis and support the alternative hypothesis. If the p-value is greater than alpha, the evidence is not strong enough to lead us to reject the null hypothesis. When we do not reject the null hypothesis, we do not accept the alternative. So, again, what this is saying is that you only accept the alternative when you reject the null. So if you do not reject the null, that means you don't accept the alternative. So should we reject the null hypothesis? The answer is no. So why? Since p-value is bigger than alpha, right? Because 0.17 is bigger than 0.05. Let me make sure I'm quoting these numbers right. Yeah. Since that's true, we fail to reject the null hypothesis. What do you conclude regarding the alternative hypothesis? We do not accept the alternative hypothesis. Write a conclusion about this hypothesis test in plain language. Okay, so we always start by stating the significance level. At a 5% significance level, the evidence suggests, so what we want to say is that the alternative is not true. So if we look at the alternative was that the majority of adults in the West region of the U.S. self-identified as pro-choice. So we do not accept that. Let me actually say it this way, right? Let me say it this way. The evidence does not suggest that the majority of U.S. adults in the West identify as pro-choice. Okay, so that is our conclusion. Next steps. Errors in hypothesis tests. In the example above, we could not support the claim that a majority of adults in the West region of the U.S. self-identified as pro-choice. The evidence did not support the claim, but sometimes evidence can be misleading. There is a small possibility that our conclusion was wrong. Even if we make no errors in the testing process, our conclusion can still be wrong. There are two types of errors in conclusions. Before I go on, this is important to note we are talking about errors that are not our fault. What does that mean? Well, remember, we are testing something with a 5% significance level, which means that 5% of the time we might be wrong because the sample that we collect may actually mislead us. What if a majority of adults did identify as pro-choice, but the sample that we got just didn't have enough people. It just didn't represent the true proportion, right? It happens, right? Sometimes you just collect an unlucky sample. So if an error like that occurs, it's not your fault. That's what we're talking about here. We're talking about errors that naturally occur because there's always a small chance. So if we reject the null hypothesis, even though it is true, we call that a type 1 error. If we fail to reject the null hypothesis, even though it is false, we make a type 2 error. The thing is, you're never going to know if you made one of these errors, right? So at the conclusion of a test, we cannot know whether we have committed an error because we do not know what is actually true. We conduct tests because we do not know. Thus, if we reject the null hypothesis, there is a chance that a type 1 error may have occurred. If we fail to reject the null hypothesis, there is a chance that a type 2 error may have occurred. So the following table summarizes the errors in a hypothesis test. So let's look at this. If the null is true, and let me use a highlighter to point this out. If the null is true but you reject the null, that's called a type 1 error. And if the null is false but you fail to reject it, in other words, you fail to reject something that you should have rejected, that's called a type 2 error. Okay? The level of significance, alpha, is related to the likelihood of these errors. Consider cases where the null hypothesis is true. When alpha is equal to 0.05, we reject a null hypothesis for sample data that occur less than 5% of the time by random chance. Thus, when the null hypothesis is true, we reject it 5% of the time, committing a type 1 error. This does not mean a type 1 error occurs in 5% of all hypothesis tests, because a type 1 error can only occur if the null hypothesis is true. So let's recap, okay? You can always make one of these errors, okay? If you rejected the null, there is a 5% chance that you made a type 1 error. And if you fail to reject the null, there's a 5% chance that you made a type 2 error. And there's no way to get those smaller except for maybe testing at a lower and lower significance level, okay? But there's always a chance that you're wrong. So that's what your alpha is, okay? The level of significance is the maximum allowable probability of making a type 1 or a type 2 error, okay? Okay. By the way, this should say type 1 or, let me fix this, or type 2 error. Right, did they call it that? Yes, okay. So try these. Consider the example about being pro-choice. We concluded that the data does not support the claim that a majority of adults in the West region of the U.S. self-identified as pro-choice. But note, the data may have led us to a wrong conclusion. If the conclusion is not correct and the true proportion is not equal to 0.50, what type of error would this be? Well, we failed to reject the null, didn't we? Right? That's what we did last time. So we failed to reject the null, even though it was true. Oh, sorry, even though it was false, I mean. So it would be a type 2 error. Right? Because we were in this category, right? We failed to reject the null, so we are in that row. So either we made the correct decision or we made a type 2 error. Okay. Okay. Consider the following null and alternative hypothesis. We're going to practice here talking about what these errors would be. So the null hypothesis for this example problem is the proportion of adults in the US who believe in UFOs is 0.25. P is equal to 0.25. By the way, guys, the code word for this lesson is UFO. Okay, so that's what you're going to put in the little box, UFO. The alternative hypothesis, the proportion of adults in the US who believe in UFOs is less than, P is less than 0.25. Okay? Describe what a type 1 error would be for these hypotheses. So remember, a type 1 error is we reject the null even though it is true. So this means we reject that the proportion of adults in the US who believe in UFOs is 0.25 even though it is true. So this would be a type 1 error. Okay? What would a type 2 error be? It's the same thing except we say we fail to reject. That the proportion of adults in the US who believe in UFOs is 0.25. So if we fail to reject it, that means that we should have rejected it, so even though it is false. Okay, so again, we reject the null even though it's true. That's called type 1. For type 2, we fail to reject the null even though it is false. Okay. All right, guys, that is it for this lesson. Thank you very much for watching. I hope it was helpful.